Hello, and welcome. I'm so glad you're here. If you've come to this quiet place tonight, it may be because the day has asked much of you, and now, as the light softens and the world begins to hush, you're looking for something gentle to carry you toward rest. That's perfectly all right. You don't need to do anything at all right now. You can simply settle in, let your shoulders drop, and allow yourself to be here, breathing slowly as we begin a journey together through one of the most peaceful topics the universe has to offer: the motion of planets as they glide through space. There's something deeply soothing about the way planets move. They follow paths that are ancient, predictable, and extraordinarily calm. They don't rush. They don't stumble. They simply continue, night after night, year after year, tracing the same graceful routes they have traveled for billions of years. And tonight, we're going to explore these motions together, slowly and softly, with no urgency at all. If you'd like to follow along for more quiet journeys like this one, you're always welcome to do so. But there's no pressure, no need to decide anything right now. Just rest and let the facts unfold like a gentle tide. Let's begin with something simple and beautiful. Every planet in our solar system moves in an ellipse. An ellipse is just a stretched circle, a shape that is soft and symmetrical, with 2 points inside called foci. The sun sits at one of those foci, glowing quietly, while the planet glides around it in a smooth, endless loop. This shape, this ellipse, is not a coincidence. It emerges naturally from the way gravity works, the way mass pulls on mass across the silence of space. And because of this, the orbit is stable. It doesn't wobble unpredictably. It doesn't spiral inward or fly apart. It simply continues, calm and constant, like a breath that never stops. The closer a planet is to the sun, the faster it moves. This might seem surprising at first, but it makes a kind of gentle sense. When a planet is near the sun, gravity pulls more strongly, and the planet responds by moving more swiftly along its path. But this speed is not frantic. It's smooth, like a river flowing downhill. Mercury, the closest planet to the sun, completes its orbit in just 88 Earth days. It moves quickly, yes, but not chaotically. It follows the same route every time, tracing its small, tight ellipse with quiet precision. There is something reassuring in that. Even the fastest orbit is still an orbit, still a pattern, still a rhythm. And then, farther out, the planets slow down. Venus takes 225 days to circle the sun. Earth takes 365, a number we know well, the length of our year. Mars takes 687 days, nearly twice as long. And as we move farther still into the realm of the giant planets, the orbits stretch out into decades and centuries. Jupiter takes nearly 12 Earth years to complete one journey around the sun. Saturn takes 29. Uranus takes 84. Neptune, the farthest planet we know, takes 165 years. If Neptune had begun its orbit on the day you were born, it would not return to that same point in space until long after your life had ended. And yet it moves. Slowly, steadily, without haste, it continues. There is no sound in space, of course. No hum of engines, no rush of wind. The planets move in perfect silence, gliding through the vacuum with nothing to slow them down. This silence is part of what makes orbital motion so peaceful. There is no friction in space, no air to push against. And so once a planet is moving, it continues to move forever, coasting along its ellipse with no effort at all. Newton understood this. He called it inertia, the tendency of an object in motion to stay in motion. A planet, once set on its path billions of years ago, simply keeps going. It doesn't need fuel. It doesn't grow tired. It moves because it has always been moving, and it will continue to move quietly for as long as the sun shines. Gravity is the only force that guides these motions. It's a gentle force, in a way, never pushing, only pulling. The sun pulls on each planet, and each planet pulls back on the sun, though the sun is so much more massive that it barely moves at all. This pull is what keeps the planet from flying off into the darkness. It curves the planet's path, bending it into that soft ellipse, holding it close without ever touching it. Gravity doesn't shout. It doesn't jerk or shove. It simply pulls steadily and quietly across millions or billions of miles, and the planet responds, falling toward the sun, but also moving sideways fast enough that it never actually arrives. This balance, this endless falling that never ends in collision, is what an orbit really is. And here's something wonderful. The time it takes for a planet to orbit the sun is related to its distance in a beautifully simple way. This relationship was discovered by Johannes Kepler more than 400 years ago, and it's one of the most elegant patterns in all of science. Kepler found that if you take the time a planet needs to complete one orbit and square it, that number is proportional to the cube of the planet's average distance from the sun. It sounds a bit mathematical, I know, but what it really means is this. The farther away a planet is, the longer its year, and the relationship between distance and time is smooth, predictable, and universal. Every planet follows this rule. Every moon around every planet follows it too. It's a kind of cosmic harmony, a rhythm that runs through the entire solar system. Kepler discovered this pattern by studying the motion of Mars. He spent years, almost a decade, analyzing the careful observations made by the astronomer Tycho Brahe, trying to understand exactly how Mars moved across the sky. At first, he tried to fit the motion into perfect circles, because circles were considered the most perfect shape, the shape the heavens should naturally follow. But the data didn't fit. Mars refused to move in a circle. And so, slowly, carefully, Kepler let go of the old idea and tried something new. He tried an ellipse, and it worked. The ellipse fit the data perfectly. Mars, it turned out, was not moving in a circle at all. It was moving in a gentle, stretched loop, and once Kepler saw that, everything else fell into place. This was a profound shift in how we understand the universe. For thousands of years, people had believed that the heavens moved in perfect circles because circles were seen as divine, unchanging, ideal. But Kepler showed that the real motion, the true motion, was something softer, something more flexible. An ellipse is not less beautiful than a circle. It's simply different. And in its own way, it's even more interesting because it allows for variation. A planet on an elliptical orbit is sometimes closer to the sun and sometimes farther away. Its speed changes, its distance changes, and yet the overall pattern remains constant. The ellipse itself doesn't change. It's a shape that holds both variety and stability at the same time. Let's think about Earth for a moment. Our planet moves around the sun in an ellipse, though it's a very gentle ellipse, almost circular. The difference between Earth's closest approach to the sun and its farthest point is only about 3%. That's a difference of roughly 5 million kilometers, which sounds like a lot, but in the scale of the solar system, it's quite small. We call the closest point perihelion and the farthest point aphelion. Earth reaches perihelion in early January and aphelion in early July. Interestingly, this means that Earth is actually closest to the sun during winter in the northern hemisphere and farthest during summer. This surprises many people because we tend to think of summer as the time when Earth is closer to the sun. But in fact, the seasons are caused not by our distance from the sun, but by the tilt of Earth's axis. It's the angle of sunlight, not the distance, that makes summer warm and winter cold. Still, even though Earth's orbit is nearly circular, it is an ellipse, and that ellipse has consequences. When Earth is closer to the sun, it moves a little faster. When it's farther away, it moves a little slower. This variation is subtle, just a small change in speed, but it's real, and it's measurable. And it's another reminder that orbits are not rigid. They breathe, they flex, they respond to the forces acting on them. And yet, they never lose their essential shape. The ellipse endures. Now let's drift outward a little away from Earth and think about the other planets. Each one has its own ellipse, its own distance, its own year, and each one moves in the same direction, counterclockwise as seen from above the sun's north pole. This is not a coincidence. All the planets formed from the same spinning disk of gas and dust that surrounded the young sun more than 4.5 billion years ago. That disk was rotating, and as the planets coalesced from the material in the disk, they inherited that rotation. They all move in the same direction because they all came from the same spinning cloud. It's a kind of family resemblance, a shared history written into their motions. And not only do the planets all move in the same direction, but they also all move in nearly the same plane. If you could look at the solar system edge-on, you'd see that the orbits of the planets are all lined up like grooves in a record, all lying flat in a thin disk. This plane is called the ecliptic, and it's the plane of Earth's orbit. The other planets' orbits are tilted slightly relative to the ecliptic, but only by a few degrees. Mercury's orbit is tilted the most, by about 7 degrees, but even that is a small angle. The overall picture is one of flatness, of alignment, of order. The solar system is not a chaotic jumble of planets flying in all directions. It's a calm, organized structure with everything moving in harmony. This flatness, this alignment, is another consequence of the solar system's origin. The spinning disk of gas and dust that formed the planets was flat because it was rotating. As the material in the disk collided and clumped together, any motion that wasn't in the plane of the disk got canceled out. What remained was motion in the plane, smooth and circular, and that motion became the orbits we see today. So when you look up at the night sky and trace the path of the planets across the zodiac, you're seeing the remnants of that ancient disk, the memory of the solar system's birth, still playing out in the motions of the planets. Let's pause here for a moment and think about what an orbit really feels like. If you were standing on a planet, you wouldn't feel the motion. You wouldn't sense the speed. Just as we don't feel Earth's motion as it travels around the sun at 30 kilometers per second, a person standing on Mars or Venus or Jupiter wouldn't feel anything either. The motion is perfectly smooth, perfectly steady. There's no acceleration in the sense of speeding up or slowing down suddenly. The changes in speed are gradual, spread out over weeks and months. And because there's no air resistance, no bumps, no friction, the ride is silent and seamless. You would simply stand there under an alien sky, and the stars would slowly wheel overhead, and you would be moving through space at thousands of kilometers per hour without feeling a thing. This is one of the most calming aspects of orbital motion. It's motion without effort, without strain. The planets don't struggle. They don't fight against anything. They simply glide, held in place by gravity, moving through the vacuum with a kind of effortless grace. And they will continue to do so for billions of years. The orbits we see today are essentially the same orbits that existed when the first life appeared on Earth. And they will be the same orbits long after we are gone. There is a deep stability here, a permanence that is rare in the universe. Most things change. Stars are born and die. Galaxies collide. Mountains rise and erode. But the orbits of the planets, for all practical purposes, are eternal. Of course, the orbits do change, but so slowly that we can barely perceive it. Over millions of years, the gravitational pull of the planets on each other causes tiny shifts in their orbits. An orbit might become slightly more elliptical or slightly more circular. Its tilt might change by a fraction of a degree. These changes are real, and over very long timescales, they can have significant effects. But on human timescales, on the timescale of a lifetime or even a civilization, the orbits are constant. They are the closest thing we have to a cosmic clock, a reliable, repeating pattern that we can count on. Let's think about Mercury again. The smallest planet, the one closest to the Sun. Mercury's orbit is the most elliptical of all the planets, with a difference of about 40% between its closest and farthest points from the Sun. When Mercury is at perihelion, it's only 46 million kilometers from the Sun. At aphelion, it's 70 million kilometers away. This is a substantial difference, and it means that Mercury experiences a much greater variation in sunlight and temperature than Earth does. But even so, Mercury's orbit is stable. It repeats over and over, every 88 days, tracing the same ellipse with the same timing. And because Mercury is so close to the Sun, we can actually observe a strange and wonderful effect in its orbit, an effect that Einstein's theory of relativity predicts. The point of Mercury's closest approach to the Sun, its perihelion, slowly shifts over time. Each time Mercury completes an orbit, the perihelion is in a slightly different place, and over many orbits, this shift adds up. The perihelion precesses, rotating around the Sun, completing a full circle in about 3 million years. Most of this precession can be explained by the gravitational pull of the other planets, especially Venus and Jupiter. But there's a tiny extra bit of precession, just 43 arcseconds per century, that couldn't be explained by Newton's laws alone. This tiny discrepancy puzzled astronomers for decades. And then, in 1915, Einstein published his general theory of relativity, which describes gravity not as a force, but as a curvature of space-time. When Einstein applied his new theory to Mercury's orbit, he found that it predicted exactly that extra 43 arcseconds of precession. It was one of the first confirmations that Einstein's theory was correct, and it came from watching the slow, patient motion of a planet as it circled the Sun. This is a beautiful example of how even the calmest, most predictable motions can reveal deep truths about the universe. Mercury doesn't shout. It doesn't announce its secrets. It simply moves quietly. And if you watch carefully enough, with enough precision, you can see the subtle effects of space-time itself, bending and warping under the influence of the Sun's mass. It's a reminder that the universe is full of hidden layers, and that patience and careful observation can uncover wonders. Now let's drift farther out, past Venus, past Earth, to Mars. Mars has an orbit that is noticeably more elliptical than Earth's. Its distance from the Sun varies by about 20% over the course of its year. This variation has real effects on the Martian climate. When Mars is closer to the Sun, it receives more sunlight, and the southern hemisphere, which is tilted toward the Sun during this time, experiences a brief, intense summer. When Mars is farther from the Sun, the climate cools. This interaction between orbital distance and axial tilt creates a more extreme seasonal cycle on Mars than we experience on Earth. And yet, even with this variation, the orbit itself is stable. Mars returns to the same points year after year, following the same elliptical path it has followed for billions of years. Mars also gives us a chance to think about orbital resonance, a phenomenon that occurs when two orbiting bodies exert regular, periodic gravitational influence on each other. Resonances are like harmonies in music, patterns where the periods of two orbits are related by simple ratios. Mars itself isn't in a strong resonance with any other planet, but its moons, Phobos and Deimos, orbit Mars in ways that are stable and predictable. Phobos, the larger and closer of the two, orbits Mars in just 7.5 hours, faster than Mars rotates. This means that from the surface of Mars, Phobos rises in the west and sets in the east, the opposite of what we see with our moon. Deimos, farther out, takes 30 hours to orbit, and from Mars, it rises and sets in the more familiar east-to-west direction. These two small moons, probably captured asteroids, have settled into stable orbits around Mars, held in place by gravity, moving in silence above the red deserts below. Beyond Mars, we come to the asteroid belt, a region of space filled with thousands upon thousands of rocky bodies, each one following its own elliptical orbit around the Sun. The asteroids are not evenly distributed. There are gaps in the belt, regions where very few asteroids are found, and these gaps are caused by orbital resonances with Jupiter. If an asteroid happens to orbit the Sun in a period that is a simple fraction of Jupiter's period, say 1/2 or 1/3, then it will feel a regular gravitational tug from Jupiter at the same point in its orbit, over and over. Over time, these repeated tugs add up, and the asteroid's orbit becomes unstable. It gets nudged into a different orbit, leaving a gap behind. These gaps are called Kirkwood gaps, named after the astronomer Daniel Kirkwood, who discovered them in the 1860s. They're a beautiful example of how gravity can sculpt the distribution of objects in space, creating patterns and structures through nothing more than patient, repeated influence. And then, beyond the asteroid belt, we come to Jupiter. Jupiter is the giant of the solar system, more massive than all the other planets combined. Its gravity dominates the outer solar system, shaping the orbits of countless smaller bodies. Jupiter's own orbit is nearly circular, and it takes just under 12 Earth years to complete. Because Jupiter is so massive, it doesn't just orbit the Sun also orbits Jupiter, in a sense. More precisely, both the Sun and Jupiter orbit their common center of mass, a point called the barycenter. For most planets, the barycenter is inside the Sun, because the Sun is so much more massive. But Jupiter is massive enough that the barycenter between it and the Sun lies just outside the Sun's surface. So as Jupiter moves around the Sun also moves in a small circle, wobbling slightly in response to Jupiter's pull. This wobble is tiny, but it's real, and it's one of the ways astronomers detect planets around other stars. By watching for the wobble of a distant star, they can infer the presence of an unseen planet, tugging on the star with its gravity. Jupiter's moons are a solar system in miniature. The four largest, Io, Europa, Ganymede, and Callisto, were discovered by Galileo in 1610, and they orbit Jupiter in periods ranging from 2 days to 17 days. These moons are locked in a beautiful set of orbital resonances. For every one orbit that Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This means that the 3 inner moons line up in the same configuration on a regular basis, and their gravitational interactions reinforce each other. These resonances are stable and have persisted for billions of years. They also have important effects on the moons themselves. The gravitational tugs cause tidal heating, especially in Io, which is squeezed and stretched by the combined pull of Jupiter and the other moons. This heating keeps Io's interior molten, and it drives the most intense volcanic activity in the solar system. Io's surface is constantly being resurfaced by eruptions, all because of the quiet, patient pull of gravity, acting through the harmony of orbital resonance. Europa, the next moon out, is also heated by tidal forces, though not as intensely as Io. Europa's surface is covered in ice, but beneath that ice, there's almost certainly a global ocean of liquid water, kept warm by tidal heating. This ocean is one of the most promising places in the solar system to search for life beyond Earth. And it exists because of an orbit, because of the way Europa moves around Jupiter, locked in resonance with its neighboring moons, flexing and heating in response to gravity's gentle, relentless pull. Farther out, we come to Saturn, the ringed planet. Taking 29 years to circle the Sun, Saturn's rings are one of the most beautiful structures in the solar system, and they too are shaped by orbital motion. The rings are made of countless small particles, each one orbiting Saturn independently. Some particles are as small as grains of sand, others are as large as houses, but all of them follow the same rules, the same laws of motion. They move in ellipses, though most of those ellipses are very nearly circular, and they move at different speeds depending on their distance from Saturn. Particles closer to Saturn move faster, particles farther out move slower. This creates a kind of shearing motion, where the inner edge of the rings moves faster than the outer edge, and the rings spread out into a thin, flat disk. The rings also contain gaps, cleared out by small moons that orbit within or near the rings. These moons are called shepherd moons because they herd the ring particles, keeping them confined to narrow bands. The gravity of a shepherd moon pushes ring particles away, creating a gap, and the gap remains as long as the moon is there. It's another example of how gravity sculpts and organizes, how the simple pull between masses can create structure and pattern. Saturn itself has more than 80 moons, each one following its own orbit. The largest, Titan, is bigger than the planet Mercury, and it takes 16 days to orbit Saturn. Titan has a thick atmosphere and lakes of liquid methane on its surface. It's a strange, cold world, but it's also a world shaped by orbital motion, by the slow dance of gravity between moon and planet. Titan's orbit is slightly elliptical, and this causes tidal forces that may help drive geological activity on its surface. Even in the cold outer reaches of the solar system, orbits matter. They shape worlds. They create conditions. They make things possible. Beyond Saturn, we come to Uranus, a planet that takes 84 years to orbit the Sun. Uranus is unusual because it's tipped over on its side. Its axis of rotation is tilted by 98 degrees, which means that its poles lie almost in the plane of its orbit. No one knows for sure why Uranus is tilted this way. The most likely explanation is that early in its history, Uranus was struck by a large object, perhaps a planet-sized body, and the collision knocked it over. But despite this dramatic tilt, Uranus's orbit is stable and predictable. It follows its ellipse year after year, moving slowly through the distant cold. And then, at the edge of the classical solar system, we come to Neptune. Neptune takes 165 years to complete one orbit. It was discovered in 1846, and it has not yet completed a full orbit since its discovery. It won't return to the same point in its orbit where it was first seen until the year 2011. Wait, that has already passed. Neptune completed its first observed orbit in 2011, quietly, without fanfare, simply continuing its ancient path. Neptune's orbit is nearly circular, and it moved through space at just over 5 kilometers per second, a leisurely pace compared to the inner planets, but still fast enough to cover vast distances. In one Earth year, Neptune travels more than 150 million kilometers, a distance equal to the space between the Earth and the Sun, yet it takes 165 years to complete its journey. Neptune has a moon called Triton, which is unusual because it orbits Neptune backward, in the opposite direction to Neptune's rotation. This retrograde orbit suggests that Triton was not formed alongside Neptune, but was captured later, pulled in by Neptune's gravity from somewhere else in the outer solar system. Triton's orbit is slowly decaying, which means that it's gradually spiraling inward toward Neptune. In a few billion years, Triton will come so close that Neptune's gravity will tear it apart, and it will form a spectacular ring system around the planet. But for now, Triton orbits peacefully, taking just under 6 days to circle Neptune, moving backward through the sky. All of these orbits, from Mercury to Neptune, from moons to asteroids, are governed by the same simple principles: gravity pulls, inertia carries. The result is an ellipse, a stable, repeating path through space. And because these principles are universal, we see the same patterns everywhere we look. Moons orbit planets. Planets orbit stars. Stars orbit the centers of galaxies. Even galaxies themselves move in great looping paths through the universe, pulled by the gravity of other galaxies and the invisible dark matter that fills space. Orbital motion is one of the fundamental rhythms of the cosmos, a pattern that repeats at every scale, from the smallest moon to the largest galaxy cluster. And here's something wonderful to consider. The orbits we see today are not arbitrary. They're the result of billions of years of evolution, of countless small interactions and adjustments. When the solar system was young, it was chaotic. There were many more objects, colliding and merging and scattering each other. But over time, the system settled. The unstable orbits were cleared out. Objects either collided with something else, or were ejected from the solar system entirely, or found stable paths that didn't intersect with anything. What remains today are the survivors, the orbits that work, the paths that can endure. The solar system we see is a system that has found its balance, and that balance is peaceful. There's also something deeply comforting in the predictability of orbits. We can calculate exactly where a planet will be thousands of years in the future, or where it was thousands of years in the past. This predictability allowed ancient astronomers to create calendars, to predict eclipses, to navigate by the stars. It allowed us to send spacecraft to distant planets, timing our launches so that the spacecraft would arrive exactly when and where we intended. The Voyager spacecraft, launched in 1977, visited Jupiter, Saturn, Uranus, and Neptune, using the gravity of each planet to fling it onward to the next. This was possible only because we understood orbital motion so well, because we could predict with exquisite precision where each planet would be years in advance. And even now, decades later, those Voyager spacecraft are still moving, still coasting through space, following their own orbits around the sun, though they're now so far away that they've left the influence of the planets behind. They're in interstellar space, the region between the stars, but they're still bound to the sun, still moving in enormously long ellipses that will take them thousands of years to complete. They're moving in silence, in darkness, carrying with them golden records inscribed with sounds and images from Earth, messages in a bottle cast into the cosmic ocean. And they move according to the same laws that govern the planets, the same gentle, inevitable pull of gravity. Let's return for a moment to Kepler and his 3 laws of planetary motion, because they summarize so much of what makes orbital motion beautiful and calming. The first law says that planets move in ellipses, with the sun at one focus. The second law says that a planet sweeps out equal areas in equal times, which means it moves faster when it's closer to the sun and slower when it's farther away. The third law says that the square of a planet's orbital period is proportional to the cube of its average distance from the sun. These 3 laws, discovered through patient observation and careful thought, describe the motion of every planet, every moon, every comet. They are simple, elegant, and universal. And they were discovered without telescopes, without computers, without any of the tools we take for granted today. They were discovered by watching the sky, night after night, and thinking deeply about what those motions meant. Kepler's second law, in particular, has a beautiful geometric quality. Imagine a line connecting a planet to the sun. As the planet moves, this line sweeps out an area, like the hand of a clock sweeping across a clock face. Kepler's second law says that this line sweeps out equal areas in equal times. So if you measure the area swept out in 1 week when the planet is close to the sun, it will be the same as the area swept out in 1 week when the planet is far from the sun. But because the planet is farther from the sun when it's at aphelion, the line is longer, and so the planet has to move a shorter distance along its orbit to sweep out the same area. This is why planets move slower when they're farther from the sun. It's a consequence of geometry and gravity working together in perfect harmony. This law also tells us something profound about the conservation of angular momentum. Angular momentum is a measure of how much rotational motion an object has, and in the absence of external forces, it's conserved. A planet orbiting the sun has angular momentum, and because there are no external forces acting on it, ignoring the tiny effects of other planets, that angular momentum stays constant. When the planet is closer to the sun, it has to move faster to conserve angular momentum. When it's farther away, it moves slower. It's the same principle that causes a figure skater to spin faster when they pull their arms in, and slower when they extend their arms out. The skater and the planet are both conserving angular momentum, and the result is a change in speed. Now, let's think about what happens when orbits interact. We've already talked about resonances, where two orbits have periods that are related by simple ratios. Resonances can be stabilizing or destabilizing, depending on the details. In some cases, a resonance locks two objects into a stable configuration that can last for billions of years. The moons of Jupiter are an example of this. In other cases, a resonance can pump energy into an orbit, making it more and more eccentric until the object is ejected or collides with something. The Kirkwood gaps in the asteroid belt are an example of this. Resonances are everywhere in the solar system, and they're one of the main ways that gravity organizes and structures the orbits of small bodies. There are also near resonances, situations where two orbits are almost, but not quite, in a simple ratio. These near resonances can cause slow, periodic changes in the orbits over time. The orbits might become more eccentric, then less eccentric, then more again, oscillating back and forth over thousands or millions of years. These oscillations are usually small, and they don't threaten the overall stability of the system, but they add a layer of complexity, a subtle variation to the otherwise steady motion. One of the most famous near resonances involves Neptune and Pluto. Pluto, now classified as a dwarf planet, orbits the Sun in 248 years, while Neptune orbits in 165 years. The ratio of these periods is very close to 3:2, which means that for every 3 orbits Pluto completes, Neptune completes almost exactly 2. This near resonance has a protective effect. Even though Pluto's orbit crosses Neptune's orbit, the two objects are never in the same place at the same time. The resonance keeps them apart, ensuring that they never collide. It's a beautiful example of how gravity can create safety through synchronization. Pluto's orbit is also highly elliptical and tilted compared to the other planets. At perihelion, Pluto is closer to the Sun than Neptune is, and at aphelion, it's much farther out. This large variation in distance means that Pluto experiences a huge range of temperatures and conditions over the course of its year. When Pluto is closest to the Sun, its thin atmosphere of nitrogen, methane, and carbon monoxide sublimates from the surface ice and forms a tenuous envelope around the planet. When Pluto is farther from the Sun, the atmosphere freezes and falls back to the surface as snow. This breathing atmosphere is driven entirely by Pluto's elliptical orbit, by the changing distance between the dwarf planet and the Sun. Beyond Neptune, there is a vast region of space called the Kuiper Belt, filled with icy bodies, remnants from the formation of the solar system. These objects, like Pluto, follow elliptical orbits, and many of them are in resonances with Neptune. Some take hundreds of years to orbit the Sun. Others take thousands. They move slowly, silently, in the cold darkness at the edge of the solar system. And yet, they follow the same laws, the same principles as the planets closer in. Gravity pulls, inertia carries, ellipses form, orbits endure. Even farther out, there is the Oort cloud, a vast, spherical shell of icy bodies that surrounds the solar system at a distance of up to a light year or more. The objects in the Oort cloud are so far from the Sun that they barely feel its gravity, and their orbits are enormous, taking millions of years to complete. These are the comets, the visitors from the deep cold, and occasionally one of them is nudged by the gravity of a passing star, and its orbit changes, sending it falling inward toward the Sun. As the comet approaches, the Sun's heat causes the ice to sublimate, forming a glowing coma and a long tail that streams out behind it. The comet swings around the Sun, following a long, narrow ellipse, and then heads back out into the darkness, not to return for thousands or millions of years. And even these comets, on their wild, looping paths, obey the same laws. They move in ellipses. They speed up as they approach the sun and slow down as they recede. They are part of the same great dance. All of this motion, all of these orbits, create a kind of cosmic clockwork, a system of interlocking rhythms and cycles. The planets return to the same positions relative to each other in patterns that repeat over thousands of years. These patterns are called planetary alignments, though the planets never truly align in a perfect straight line. But they do come in certain configurations, and these configurations repeat slowly and patiently as the planets move through their orbits. Ancient astronomers noticed these patterns and used them to create calendars and to predict events. They saw the sky as a great clock, and in a sense, they were right. The sky is a clock, the most reliable clock we have, driven by gravity and inertia, ticking away the centuries with perfect regularity. And you, lying here listening to these words, are part of this system too. You live on a planet that is moving through space, tracing its ellipse around the sun. Right now, as you rest, Earth is traveling at 30 kilometers per second, carrying you with it. You don't feel it, of course. The motion is too smooth, too steady, but it's happening. You are moving through space, held gently by gravity, following a path that has been followed for billions of years and will continue for billions more. There's something profoundly peaceful in that thought. You are part of something vast and ancient and enduring. You are orbiting the sun, just as the moon orbits Earth, just as the planets orbit the sun, just as the sun orbits the center of the galaxy. Motion within motion, circles within circles, all moving together in a great, silent harmony. The pull of gravity reaches everywhere, and yet it never shouts. It simply holds quietly and constantly, drawing bodies toward one another across the dark. Every planet feels this gentle tug from the sun, and in turn, the sun feels the whisper of each planet pulling back. This is the beauty of gravitational interaction. It is mutual, patient, and perfectly balanced. No force is wasted. No motion is random. Everything responds to everything else. And the result is a dance that has continued for billions of years without faltering. When we speak of orbits, we often imagine the planet as a small traveler circling a massive, unmoving sunday. But in truth, both bodies move. The sun itself shifts slightly, swaying in response to the planets that orbit it. Jupiter, being the most massive planet, tugs the sun more than any other. The center of mass between Jupiter and the sun lies just outside the sun's surface, and so the sun wobbles gently as Jupiter completes its long journey around it. This shared motion is called the barycenter, and it reminds us that even the mightiest star is not entirely still. The barycenter is the point in space where two orbiting bodies balance each other. For smaller planets, this point lies deep within the sun, almost at its core. For Jupiter, it floats just beyond the solar surface. If you could watch the solar system from a great distance, you would see the sun tracing a small, looping path through space, nudged by the gravitational presence of its planets. It is a quiet reminder that orbits are not one-sided. They are conversations, written in motion. This mutual pull extends beyond planets and stars. Moons orbit planets, and in doing so, they tug back. The Earth and the Moon orbit a common barycenter located inside the Earth, about 3/4 of the way from the center to the surface. As the Moon circles our world, the Earth wobbles slightly in response. This wobble is small, but it is real, and it influences everything from the tides to the subtle drift of our planet's rotation. The Moon does not simply follow the Earth. They move together, bound by invisible threads of gravity. Even asteroids and comets participate in this silent conversation. As they pass near a planet, their paths bend. The planet's gravity reaches out and curves their trajectory, sending them off in a new direction. Sometimes the asteroid speeds up, sometimes it slows down, depending on the angle of approach. The planet, too, feels a tiny tug in return, though its great mass means the effect is almost imperceptible. But it is there. Every encounter leaves a trace, a tiny adjustment in momentum that ripples outward through time. Orbital motion is often described as falling without ever hitting the ground. This is more than a metaphor. It is the literal truth. A planet moves forward through space while simultaneously falling toward the sun. But because it is moving sideways fast enough, it never arrives. It simply continues to fall, tracing a smooth curve through the void. There is no friction to slow it, no air to resist it, and so it falls forever in the most peaceful way imaginable. This kind of motion requires no fuel, no effort, no thought. Once an orbit is established, it continues on its own. The planet does not need to remember where to go or how fast to travel. The laws of motion and gravity take care of everything. It is a system that runs on pure geometry, on a relationship between speed, distance, and mass. And because those relationships are stable, the orbit remains stable. Year after year, millennium after millennium, the path repeats. There is something deeply calming in this constancy. We live on a world that is always moving, always falling, and yet we feel no danger. The ground beneath us is steady. The sky above us is predictable. We can look up at night and know where the planets will be, not just tonight, but 100 years from now. This predictability is not a limitation. It is a gift. It allows life to flourish, seasons to cycle, and time to unfold in an orderly way. The speed of a planet in its orbit is not arbitrary. It is determined by its distance from the sun. The closer a planet is, the faster it must move to maintain its orbit. This is because gravity grows stronger with proximity. A planet near the sun feels a powerful pull inward, and so it must race along its path to avoid spiraling in. A planet far from the sun feels only a gentle tug, and so it drifts more slowly, taking its time. This relationship between distance and speed is one of the fundamental harmonies of the solar system. Mercury, the closest planet, hurtles along at nearly 47 kilometers per second. It completes an orbit in just 88 Earth days, moving with an urgency that matches its nearness to the sun. Venus, farther out, travels at about 35 kilometers per second, taking 225 days to circle once. Earth, at a comfortable distance, moves at roughly 30 kilometers per second, completing its journey in 1 year. Mars, more distant still, slows to 24 kilometers per second, taking nearly 2 Earth years to finish its orbit. And so the pattern continues, each planet moving at the speed that matches its place in the cosmic order. This variation in speed is not a flaw or an accident. It is a direct consequence of the way gravity works. The force of gravity weakens with distance, following an inverse square law. If you double the distance from the sun, the gravitational pull becomes 4 times weaker. If you triple the distance, it becomes 9 times weaker. This gentle fading of force allows the outer planets to move more slowly, more leisurely, as if they have all the time in the world. And in a sense, they do. Jupiter takes nearly 12 Earth years to complete 1 orbit. Saturn takes about 29. Uranus takes 84. Neptune takes 165. These are long, slow journeys, measured not in days or months, but in human lifetimes. A person born when Neptune began its orbit will be elderly by the time it returned to the same position. And yet, from Neptune's perspective, this is simply 1 year. Time, like motion, is relative. It stretches and compresses depending on where you stand. There's a certain poetry in the way the outer planets drift. They move through space with a calm that mirrors the cold and quiet of their distant realms. They are not hurried. They are not anxious. They simply glide, following the path that gravity has laid out for them, tracing enormous circles through the dark. Their moons accompany them, small companions on a vast journey, each one locked in its own orbit, each one contributing to the intricate gravitational ballet. The orbits of planets are not perfectly circular, as we have seen, but elliptical. Yet many of these ellipses are so close to circular that the difference is barely noticeable. Venus, for instance, has an orbital eccentricity of only 0.007, making its path one of the most circular in the solar system. Earth's eccentricity is 0.017, also quite low. These near-circular orbits contribute to the stability of our climates and the regularity of our seasons. The distance between Earth and the Sun changes only slightly throughout the year, and so the amount of sunlight we receive remains fairly constant. Mars, with an eccentricity of 0.093, experiences more variation. At its closest approach to the Sun, called perihelion, Mars receives significantly more solar energy than at its farthest point, aphelion. This difference affects the Martian climate, creating more extreme seasonal changes than we experience on Earth. Dust storms on Mars are more common during southern summer, when the planet is closest to the Sun and the atmosphere heats up. The shape of the orbit, then, influences not just the path of the planet, but the weather and conditions on its surface. Mercury's eccentric orbit, at 0.206, means it experiences even greater variation. At perihelion, Mercury is about 46 million kilometers from the Sun. At aphelion, it is about 70 million kilometers away. This is a substantial difference, and it affects the intensity of sunlight the planet receives. Mercury's surface temperature can vary by hundreds of degrees depending on where it is in its orbit and whether a given spot is in sunlight or shadow. The ellipse, in this case, creates a world of extremes. Yet even in these extremes, there is order. The orbit does not wobble unpredictably. It does not suddenly stretch or shrink. The ellipse remains stable, its shape determined by the initial conditions of Mercury's formation and the gravitational influence of the Sun. Over millions of years, the orbit does change slightly, influenced by the gravitational tugs of other planets. But these changes are slow and gradual. They unfold over timescales that dwarf human history. The concept of orbital resonance brings another layer of calm order to the solar system. Resonance occurs when two orbiting bodies exert regular, periodic gravitational influence on each other. This happens when their orbital periods are related by a simple ratio, such as 2:1 or 3:2. When bodies are in resonance, their gravitational tugs reinforce each other at regular intervals, creating a stable, repeating pattern. Far from being chaotic, resonance often stabilizes orbits, locking bodies into predictable relationships. One of the most beautiful examples of resonance is found in the moons of Jupiter. Three of Jupiter's largest moons, Io, Europa, and Ganymede, are locked in a 1:2:4 resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. This means that the three moons return to the same relative positions at regular intervals, creating a repeating gravitational dance. The resonance helps to maintain the orbits and also generates tidal heating within the moons, keeping them geologically active. Io, the innermost of the three, is the most volcanically active body in the solar system. Its orbit is constantly tugged by Europa and Ganymede, causing Io's shape to flex and squeeze as it moves. This tidal flexing generates heat within the moon, melting rock and driving volcanic eruptions. The resonance, then, is not just a mathematical curiosity. It has real, physical consequences. It shapes the surfaces of worlds, drives geological processes, and creates environments that might, in some cases, support life. Europa, too, benefits from this resonance. The tidal forces acting on it are strong enough to keep its interior warm, maintaining a liquid ocean beneath its icy crust. This ocean is one of the most promising places in the solar system to search for extraterrestrial life. The resonance with Io and Ganymede helps to sustain the conditions that make this ocean possible. In this way, orbital mechanics and biology are connected, linked by the invisible threads of gravity. Resonances are found throughout the solar system. Neptune and Pluto are in a 3:2 resonance. For every 3 orbits Neptune completes, Pluto completes 2. This relationship prevents the two bodies from ever colliding, even though their orbits cross when viewed from certain angles. The resonance ensures that whenever Pluto is near Neptune's orbital path, Neptune is always far away on the other side of the Sun. It is a kind of cosmic courtesy, a built-in safety mechanism that has lasted for billions of years. The asteroid belt, too, shows the influence of resonance. Certain regions of the belt are nearly empty, swept clear by the gravitational influence of Jupiter. These gaps, called Kirkwood gaps, occur at distances where an asteroid's orbital period would be in resonance with Jupiter's. At these locations, the repeated gravitational tugs from Jupiter add up over time, gradually nudging asteroids into different orbits. The result is a belt with structure, with gaps and clusters, shaped by the patient hand of resonance. Even the rings of Saturn show resonance effects. Small moons called shepherd moons orbit just inside and outside some of Saturn's rings, their gravity helping to confine the ring particles to narrow bands. The moon Prometheus, for example, orbits just inside the F ring, while Pandora orbits just outside. Together, they create a gravitational corridor that keeps the ring particles in place. The resonance between the moons and the ring particles maintains the sharpness of the ring's edges, preventing it from spreading out over time. All of this structure, all of these patterns, arise from the simple, universal law of gravity. There is no guiding intelligence, no external plan, just mass, distance, and motion interacting according to rules that never change. And yet the result is a system of breathtaking complexity and beauty, full of rhythms and harmonies that seem almost musical. It is as if the solar system is playing a symphony, written in the language of mathematics, performed on the stage of space. Orbital inclination is another factor that adds variety to planetary motion. Most planets orbit the Sun in roughly the same plane, called the ecliptic. This is because the solar system formed from a flat, rotating disk of gas and dust. As the disk collapsed, the planets that formed within it inherited its flatness. But not all orbits lie perfectly within this plane. Each planet's orbit is tilted slightly, inclined at a small angle to the ecliptic. Earth's orbital plane defines the ecliptic itself, so by definition, Earth's inclination is 0. But Mercury's orbit is inclined by about 7 degrees. Venus is inclined by about 3.4 degrees. Mars by 1.85 degrees. These small tilts mean that the planets do not all move in exactly the same flat sheet. Instead, they weave slightly above and below the ecliptic as they orbit, creating a gently undulating pattern when viewed from the side. The outer planets also have inclinations, though most are small. Jupiter's inclination is only 1.3 degrees. Saturn's is 2.5 degrees. Uranus is 0.77 degrees. Neptune is 1.77 degrees. These small angles reflect the orderly formation of the solar system, the shared heritage of the primordial disk. But they also allow for slight variations, small departures from perfect flatness that add richness to the system's geometry. Pluto, no longer classified as a planet but still a beloved member of the solar system, has a much larger inclination of about 17 degrees. This steep tilt is one of the reasons Pluto was reclassified as a dwarf planet. Its orbit does not conform to the neat, flat pattern of the 8 major planets. Instead, it cuts across the ecliptic at a sharp angle, rising high above and dipping far below the plane. This gives Pluto a unique, independent character, as if it follows its own rules. The inclination of an orbit affects when and where a planet can be seen from Earth. Planets with low inclinations stay close to the ecliptic, which means they appear along a narrow band in our sky, following the path of the Sun and Moon. This band is called the zodiac, and it has been recognized by cultures around the world for thousands of years. The predictable motion of planets through the zodiac allowed ancient astronomers to track time, predict seasons, and navigate the world. Orbital inclination also affects the likelihood of planetary transits, those rare events when a planet passes directly between Earth and the Sun. Because Mercury and Venus have inclined orbits, they do not transit the Sun every time they pass between us and our star. They must be at the right point in their orbit, where their path crosses the ecliptic, for a transit to occur. These moments are called nodes, and transits can only happen when a planet is near a node at the same time it passes between Earth and the Sun. Mercury transits occur about 13 times per century. Venus transits are much rarer, occurring in pairs separated by 8 years, with more than a century between each pair. The last Venus transit was in 2012, and the next will not occur until 2117. These transits are beautiful, peaceful events. The planet appears as a small, dark dust slowly crossing the face of the Sun, a reminder of the vast scales involved and the precise geometry required for such an alignment. The concept of orbital nodes applies to all orbiting bodies. A node is the point where an orbit crosses a reference plane, such as the ecliptic. There are 2 nodes for each orbit. The ascending node, where the body crosses from below the plane to above, and the descending node, where it crosses from above to below. These nodes are fixed points in space, at least over short time scales, and they play an important role in predicting eclipses, transits, and other alignment events. Eclipses themselves are a form of orbital alignment. A solar eclipse occurs when the Moon passes between Earth and the Sun, casting a shadow on our planet. A lunar eclipse occurs when Earth passes between the Sun and the Moon, casting a shadow on the lunar surface. Both types of eclipse require precise alignment, and both depend on the Moon being near one of its orbital nodes. If the Moon's orbit were not inclined to the ecliptic, we would experience eclipses every month. But because of the inclination, eclipses are rare and special, occurring only a few times each year. The Moon's orbit around Earth is inclined by about 5 degrees to the ecliptic. This small tilt is enough to prevent most new moons and full moons from producing eclipses. The Moon usually passes above or below the Sun's position in the sky during a new moon, and above or below Earth's shadow during a full moon. Only when the Moon is near a node, and the alignment is just right, does an eclipse occur. This makes eclipses events of precise timing and geometry, predictable yet precious. The ancient astronomers who studied eclipses discovered that they follow a repeating cycle called the Saros cycle. This cycle lasts about 18 years, 11 days, and 8 hours. After one Saros period, the Sun, Earth, and Moon return to nearly the same relative positions, and a similar eclipse occurs. By tracking these cycles, ancient cultures could predict eclipses with remarkable accuracy, even without understanding the underlying physics. The regularity of orbital motion made this possible. The sky, for all its vastness, follows patterns that can be learned and trusted. The tilt of Earth's axis, separate from its orbital inclination, also plays a crucial role in our experience of the sky. Earth's axis is tilted about 23.5 degrees relative to the plane of its orbit. This axial tilt is responsible for the seasons. As Earth orbits the Sun, different parts of the planet receive more or less direct sunlight, depending on the time of year. In June, the northern hemisphere is tilted toward the Sun, creating summer. In December, it is tilted away, creating winter. The southern hemisphere experiences the opposite pattern. This tilt is stable over human timescales, but it does change slowly over tens of thousands of years due to gravitational interactions with the Moon and other planets. The angle of the tilt varies between about 22 and 25 degrees over a cycle of roughly 41,000 years. This variation affects the intensity of the seasons and is one of the factors that influences Earth's long-term climate cycles, including ice ages. Even the tilt of our axis, then, is part of the orbital story, part of the slow, patient dance of gravity and motion. The concept of orbital energy helps us understand why orbits are stable. An orbiting body has two kinds of energy: kinetic energy, due to its motion, and gravitational potential energy, due to its position in the Sun's gravitational field. The total orbital energy is the sum of these two. In a stable orbit, this total energy remains constant. The planet may speed up or slow down as it moves through its ellipse, trading kinetic energy for potential energy and back again, but the total never changes. At perihelion, when the planet is closest to the Sun, it moves fastest. Its kinetic energy is high, but its potential energy is low because it is deep in the Sun's gravitational well. At aphelion, when the planet is farthest from the Sun, it moves slowest. Its kinetic energy is low, but its potential energy is high. The trade-off is exact. The energy lost in one form is gained in the other. This conservation of energy is one of the fundamental principles of physics, and it ensures that orbits remain stable over time. If a planet were to suddenly lose energy, perhaps by colliding with another body or passing through a cloud of gas, its orbit would change. It would spiral inward, moving to a lower orbit with less total energy. Conversely, if it gained energy, it would move to a higher orbit. But in the vacuum of space, there is nothing to take energy away or add it. The planet simply continues, its energy conserved, its path unchanging. This is why the solar system has remained stable for billions of years, and why it will likely remain stable for billions more. The gravitational influence of other planets does cause small, gradual changes in orbits over long periods. These changes are called perturbations, and they're the subject of a field called celestial mechanics. Perturbations can cause an orbit's eccentricity to increase or decrease, its inclination to shift, or its orientation in space to slowly rotate. These effects are tiny from year to year, but over millions of years, they can add up. One of the most famous examples of perturbations is the precession of Mercury's orbit. Mercury's elliptical orbit does not stay fixed in space. Instead, the entire ellipse slowly rotates, or precesses, around the Sun. Most of this precession can be explained by the gravitational influence of the other planets, especially Venus, Earth, and Jupiter. But a small part of the precession could not be explained by Newtonian gravity alone. This tiny discrepancy was one of the first pieces of evidence for Einstein's theory of general relativity, which describes gravity not as a force, but as a curvature of space-time. General relativity predicts that the intense gravitational field near the Sun causes space-time to curve more sharply, and this curvature affects the motion of nearby objects. Mercury, being the closest planet, feels this effect most strongly. The additional precession predicted by general relativity matches observations perfectly, providing powerful confirmation of Einstein's theory. Even in the calm, predictable motions of the planets, there are subtle hints of the deeper structure of the universe. The orbits of the planets are not only stable, but also resonant with the history of the solar system. Each orbit carries information about the conditions under which the planet formed. The spacing of the planets, their masses, their compositions, and their orbital properties all tell a story about the early solar system, when a disk of gas and dust surrounded the young sun. By studying orbits today, we can look back in time and reconstruct the events of 4.6 billion years ago. The process of planet formation began with tiny grains of dust colliding and sticking together in the protoplanetary disk. Over time, these grains grew into pebbles, then boulders, then planetesimals, objects kilometers across. The planetesimals continued to collide and merge, eventually forming the cores of planets. In the inner solar system, where temperatures were high, only rocky materials could condense, leading to the formation of the terrestrial planets. In the outer solar system, where it was cold enough for ice to form, the planets grew much larger, becoming the gas and ice giants. As the planets grew, they began to influence each other gravitationally. Their orbits shifted, sometimes dramatically. Some planetesimals were flung out of the solar system entirely. Others were scattered inward, where they collided with the growing planets. This period of chaos and rearrangement lasted for tens of millions of years, but eventually, the system settled into a more stable configuration. The orbits we see today are the result of that long process of adjustment, a process driven by gravity and motion. One of the most intriguing ideas in planetary science is the concept of planetary migration. This is the idea that planets can move from one orbit to another over time, driven by interactions with a disk of gas and dust, or by gravitational interactions with other planets. Evidence suggests that the giant planets of our solar system may have migrated significantly in the early history of the solar system. Jupiter, for example, may have formed farther from the Sun and then moved inward before being pulled back out by interactions with Saturn. This migration would have had profound effects on the inner solar system. As Jupiter moved, it would have scattered countless asteroids and comets, sending some crashing into the inner planets. This period, called the Late Heavy Bombardment, may have occurred about 4 billion years ago, and it may have delivered water and organic molecules to Earth, setting the stage for the emergence of life. The orbits of the planets, then, are not just paths through space. They are part of the story of life itself. The stability of our current orbits is a gift. The planets are spaced in such a way that their gravitational influences balance out. They do not pull each other into chaotic, colliding paths. Instead, they maintain a kind of gravitational harmony, each one contributing to the overall stability of the system. This is not guaranteed. In other star systems, planets can have highly eccentric orbits, or orbits that cross each other, leading to instability and collisions. Our solar system is calm, orderly, and safe, and that is one reason life has been able to flourish here. The concept of the habitable zone is closely related to orbital motion. The habitable zone is the region around a star where conditions are right for liquid water to exist on a planet's surface. This zone depends on the star's brightness and the planet's distance from the star. For our Sun, the habitable zone extends from roughly 0.95 to 1.37 astronomical units, a range that includes Earth's orbit. Venus is too close, and Mars is near the outer edge. The fact that Earth's orbit lies comfortably within this zone is one of the reasons our planet can support life. But the habitable zone is not a fixed ring. It changes over time as the star evolves. The Sun is gradually getting brighter as it ages, and this means the habitable zone is slowly moving outward. Billions of years from now, Earth's orbit may no longer lie within the habitable zone, and the planet may become too hot for life. Mars, on the other hand, may move into the zone, potentially becoming a more hospitable world. Orbital motion and stellar evolution are intertwined, shaping the long-term fate of planets. The motion of planets also affects the way we measure time. The length of a year is defined by Earth's orbital period, the time it takes to complete one orbit around the Sun. This period is about 365.25 days, which is why we have leap years to keep our calendar in sync with the seasons. But other planets have different years. A Martian year is about 687 Earth days. A Jovian year is about 4,333 Earth days. If we lived on another planet, our sense of time would be shaped by that world's orbital motion. The concept of a day is also related to motion, though in this case, it is the rotation of the planet on its axis, not its orbit around the Sun. Earth rotates once every 24 hours, giving us the cycle of day and night. But this rotation is gradually slowing down due to tidal interactions with the Moon. Billions of years ago, Earth's day was much shorter, perhaps only a few hours long. In the distant future, Earth's rotation will slow even further, and a day may last as long as a month. The dance between rotation and orbital motion is another example of the slow, patient changes that shape our world. The Moon's orbit around Earth is also slowly changing. Tidal forces cause the Moon to gradually move away from Earth at a rate of about 3.8 centimeters per year. This is a tiny amount, but over millions of years, it adds up. In the distant past, the Moon was much closer, and it appeared much larger in the sky. Total solar eclipses were more common and lasted longer. In the distant future, the Moon will be farther away, and total solar eclipses will no longer be possible. The Moon will appear too small to completely cover the Sun. The slow drift of the Moon's orbit is a reminder that even the most stable systems change over time. The concept of escape velocity is related to orbital motion. Escape velocity is the speed an object must reach to break free from a planet's or star's gravitational pull. For Earth, this speed is about 11.2 kilometers per second. If you launch a spacecraft at this speed, it will escape Earth's gravity and enter a solar orbit. If you launch it slower, it will fall back to Earth or enter an orbit around the planet. The balance between speed and gravity determines whether an object orbits, escapes, or falls. Spacecraft use this principle to travel between planets. They are launched from Earth at high speed, entering an orbit around the Sun. By carefully adjusting their speed and direction, they can be sent to intercept other planets. This requires precise calculation and timing, but it is all based on the same principles that govern natural orbits. The spacecraft follows an elliptical path, just like a planet, and arrives at its destination months or years later. The journey is long, but it is predictable, and it relies on the calm, unchanging laws of orbital motion. Gravity assists, or slingshot maneuvers, are another elegant application of orbital mechanics. When a spacecraft passes close to a planet, it can use the planet's gravity to change its speed and direction. The spacecraft falls toward the planet, swings around it, and is flung out in a new direction, moving faster than before. The planet, in turn, loses a tiny amount of orbital energy, though the effect is so small it is unmeasurable. This technique has been used to send spacecraft to the outer planets and beyond, allowing them to travel farther and faster than would otherwise be possible. The Voyager spacecraft, launched in 1977, used gravity assist from Jupiter and Saturn to reach Uranus and Neptune. These encounters allowed Voyager 2 to visit all 4 giant planets in a single mission, a feat that would have been impossible without the gravitational help. Today, both Voyager spacecraft are in interstellar space, still moving, still sending back data, carried by the momentum they gained from those long-ago encounters. Their journey is a testament to the power and elegance of orbital mechanics. The dance of orbital mechanics continues in ways both subtle and profound, revealing patterns that have persisted for billions of years. When we look closely at how planets move, we discover that their orbits are not isolated paths, but part of an interconnected web of gravitational influence. Each world tugs gently on its neighbors, creating ripples that spread through the solar system like quiet waves across a still pond. These perturbations, as astronomers call them, are usually small, barely noticeable over human lifetimes, but over millions of years they accumulate into meaningful changes. The orbits slowly shift, precess, and wobble in response to these endless gravitational conversations between worlds. The perihelion of a planet's orbit, that closest point to the Sun, does not remain fixed in space, but gradually rotates around the Sun over vast stretches of time. This phenomenon, known as apsidal precession, occurs because the gravitational pull from other planets adds tiny nudges to each orbit, causing the ellipse itself to slowly rotate. Mercury's perihelion, for instance, advances by about 574 arcseconds per century, a small but measurable drift that puzzled astronomers for decades. Most of this precession can be explained by the gravitational influence of Venus, Earth, Jupiter, and the other planets, but a tiny remainder of about 43 arcseconds per century could not be accounted for by Newton's laws alone. It was Einstein's general theory of relativity that finally explained this residual precession, showing that the curvature of space-time near the Sun's immense mass affects the motion of Mercury in ways that classical physics could not predict. This quiet discrepancy became one of the first confirmations of relativity, a whisper from the universe that space and time are woven together in ways more subtle than we had imagined. Earth's own orbit undergoes a gentle precession as well, though of a different kind. The orientation of Earth's rotational axis slowly traces a circle in the sky, completing one full cycle approximately every 26,000 years. This axial precession, sometimes called the precession of the equinoxes, means that the North Star has not always been Polaris and will not always be. In ancient Egyptian times, the star Thuban in the constellation Draco served as the pole star, and in about 12,000 years, the bright star Vega will take on that role. This slow wobble is caused primarily by the gravitational pull of the Moon and Sun on Earth's equatorial bulge, a gentle reminder that even our planet's orientation in space is subject to the patient influence of celestial mechanics. The precession changes which constellations appear in which seasons and subtly shifts the timing of the equinoxes relative to Earth's position in its orbit, a cycle that ancient astronomers noticed and tracked with remarkable precision. Beyond precession, Earth's orbit experiences variations in its eccentricity over cycles lasting about 100,000 years. Sometimes the orbit becomes slightly more elliptical, and at other times it becomes more circular, oscillating gently between these states under the gravitational influence of Jupiter and Saturn. Currently, Earth's orbit is relatively circular, with an eccentricity of about 0.0167, but this value drifts slowly over time. When the orbit is more eccentric, the difference in solar radiation received at perihelion and aphelion becomes more pronounced, subtly affecting climate patterns. These long-term orbital variations, combined with changes in axial tilt and precession, form what are known as Milankovitch cycles, named after the Serbian scientist who studied them. These cycles are thought to play a role in the timing of ice ages, as they modulate the amount and distribution of sunlight reaching Earth's surface over tens of thousands of years. The connection between orbital mechanics and climate is a beautiful example of how the quiet mathematics of celestial motion can have profound effects on the living world. The tilt of Earth's axis, currently about 23.5 degrees, also varies slowly over time, oscillating between roughly 22.1 and 24.5 degrees over a cycle of about 41,000 years. This variation in obliquity affects the severity of the seasons. When the tilt is greater, summers and winters become more extreme. When the tilt is smaller, the seasons are milder. Right now, Earth's axial tilt is slowly decreasing, moving toward the lower end of this range. The Moon plays a stabilizing role in this process, keeping the variations relatively small. Without the moon's gravitational influence, Earth's axial tilt could vary much more dramatically, potentially swinging by tens of degrees over shorter timescales, which would create chaotic and extreme climate shifts. The moon, in its quiet orbit, acts as a gentle anchor, helping to maintain the stable conditions that have allowed complex life to flourish on Earth. The concept of orbital stability extends far beyond our own planet. Astronomers have discovered that planetary systems can exist in configurations that are stable for billions of years, but only if the planets are spaced in certain ways. If two planets orbit too closely to one another, their mutual gravitational perturbations can grow over time, eventually leading to collisions or ejections from the system. There is a critical spacing, often described in terms of mutual Hill radii, that determines whether orbits will remain stable. In our solar system, the planets are spaced in such a way that their orbits have remained stable for over 4 billion years, a testament to the orderly outcome of the solar system's formation. Computer simulations show that even small changes in the positions or masses of the planets could lead to instability over millions of years, with orbits crossing and worlds colliding. The fact that we live in a stable system is not mere luck, but the result of a long process of gravitational sorting and settling that occurred in the early solar system. Some planetary systems discovered around other stars exhibit configurations that seem precarious by comparison. Hot Jupiters, for example, orbit extremely close to their parent stars, often closer than Mercury is to our Sun, and complete their orbits in just a few days. These massive planets likely formed farther out and then migrated inward, possibly through interactions with the protoplanetary disk or through gravitational encounters with other planets. In some cases, multiple planets may have existed in the system originally, but only one or two survived the migration process, with the others ejected into interstellar space or consumed by the star. The discovery of such diverse planetary architectures has revealed that our solar system's orderly, stable arrangement is just one of many possible outcomes. Yet even in these exotic systems, the same fundamental laws of orbital mechanics apply, and the surviving planets settle into configurations that are, at least for now, stable. The concept of a mean motion resonance takes on additional beauty when we consider how it can protect planets from close encounters. In a resonance, the regular timing of gravitational tugs can actually prevent planets from coming too close to one another. Jupiter and Saturn, for instance, are not in a perfect resonance, but they do experience a near resonance that causes their orbits to interact in complex ways. Every 20 years or so, Jupiter and Saturn align in the sky as seen from Earth, an event known as a Great Conjunction. The gravitational interaction during these alignments causes small periodic changes in their orbits, but because the interaction is regular and predictable, it does not lead to instability. Instead, the two giant planets have settled into a configuration where their mutual perturbations average out over time, maintaining the overall stability of the outer solar system. Orbital resonances also play a role in the structure of Saturn's rings. The rings are not uniform but contain gaps and divisions caused by the gravitational influence of Saturn's many moons. The most famous of these is the Cassini division, a wide gap in the rings located at a distance where ring particles would orbit Saturn twice for every orbit of the moon Mimas. Particles in this region are gradually nudged by Mimas's gravity, and over time, these repeated tugs clear out the gap. The result is a beautiful pattern of rings and gaps, a visible manifestation of orbital resonance on a grand scale. Similar resonances create narrower gaps and even maintain the sharp edges of some rings, with small moons acting as shepherds that confine the ring particles to specific regions. The entire ring system is a dynamic, ever-shifting structure held in place by the quiet, persistent influence of gravity and motion. The rings of Saturn also demonstrate another calming principle of orbital mechanics, the concept of tidal forces and the Roche limit. If a moon or other object ventures too close to a massive planet, the difference in gravitational pull between the near side and far side of the object becomes so great that tidal forces can tear it apart. The distance at which this occurs is called the Roche limit, and it varies depending on the densities of the planet and the object. Saturn's rings lie within the planet's Roche limit, which is why they consist of countless small particles rather than coalescing into a single moon. Any large object that strayed too close would be gently pulled apart by tidal forces, its material spreading into a ring around the planet. This process is not violent, but gradual, a quiet disassembly driven by the mathematics of gravity. The rings we see today may be the remnants of a moon that wandered too close, or they may be primordial material that never coalesced in the first place, held in this delicate state by the balance of forces. Tidal forces also affect the orbits of moons in more subtle ways. When a moon orbits a planet, tidal forces cause both the planet and the moon to bulge slightly toward each other. If the moon is in a synchronous orbit, rotating once per orbit, so that the same face always points toward the planet, the bulge on the moon remains aligned with the planet, and no energy is lost. But if the moon rotates faster or slower than it orbits, the bulge is carried out of alignment, and the gravitational pull on the bulge exerts a torque that gradually changes the moon's rotation. Over time, tidal forces slow the moon's rotation until it becomes locked, with one face perpetually facing the planet. This is why we always see the same side of our moon. The process is slow and gentle, taking millions of years, but it is inexorable. Many moons in the solar system are tidally locked to their planets, a testament to the patient work of gravity over deep time. Tidal forces also transfer energy between a planet and its moon, causing the moon's orbit to gradually change. In the case of Earth and the moon, tidal forces raised by the moon and Earth's oceans create a bulge that is carried ahead of the moon by Earth's rotation. The gravitational pull of this bulge pulls the moon forward in its orbit, causing it to slowly spiral outward. At the same time, the moon's gravity pulls back on the bulge, slowing Earth's rotation. The result is that Earth's day is gradually lengthening, and the moon is slowly receding from Earth at a rate of about 3.8 centimeters per year. Billions of years ago, the moon was much closer, and Earth's day was much shorter, perhaps only 5 or 6 hours long. Over time, the two bodies have settled into a more relaxed configuration, and this process will continue far into the future. Eventually, in billions of years, Earth's rotation will slow to the point where one side of the planet always faces the moon, just as one side of the moon always faces Earth now. The two will be mutually tidally locked, orbiting each other in a stately, synchronized dance. This same process occurs throughout the solar system. Pluto and its largest moon, Charon, are already mutually tidally locked. Charon orbits Pluto once every 6.4 days, and Pluto rotates once every 6.4 days as well. So the same face of Pluto always looks at Charon, and the same face of Charon always looks at Pluto. From one side of Pluto, Charon hangs motionless in the sky, never rising or setting. From the other side of Pluto, Charon is never visible at all. This configuration is the endpoint of tidal evolution, a state of perfect balance and minimal energy. It is a reminder that orbital mechanics naturally tends towards stability and equilibrium, with systems gradually settling into the most relaxed configurations allowed by the laws of physics. The concept of orbital energy helps us understand why these processes unfold the way they do. Every orbiting object has a specific amount of orbital energy, which is the sum of its kinetic energy due to its motion and its gravitational potential energy due to its position in the gravitational field. For a stable orbit, this total energy is negative, meaning the object is bound to the body it orbits. The more negative the energy, the more tightly bound the orbit. When tidal forces transfer energy from a planet's rotation to a moon's orbit, the moon gains energy and moves to a higher, more distant orbit. Conversely, if a moon loses energy, perhaps through interactions with a disk of material or other moons, it spirals inward. This exchange of energy is gradual and follows strict mathematical rules, ensuring that the total energy and angular momentum of the system are conserved. The predictability of these exchanges is part of what makes orbital mechanics so soothing. Nothing is arbitrary, and every change follows from clear, understandable principles. Angular momentum, the measure of an object's rotation and orbital motion, is one of the most conserved quantities in the universe. In an isolated system, angular momentum cannot be created or destroyed, only transferred from one part of the system to another. This principle governs the formation of planetary systems, the evolution of orbits, and even the behavior of galaxies. When a cloud of gas and dust collapses to form a star and planets, any initial rotation in the cloud is preserved and amplified as the material contracts. This is why planets orbit in the same direction and roughly the same plane. They inherited their motion from the rotating disk of material from which they formed. The conservation of angular momentum also explains why figure skaters spin faster when they pull in their arms, and why a planet moves faster when it is closer to the sun. These connections between the everyday and the cosmic remind us that the same physical laws apply everywhere, from the ice rink to the outer reaches of the solar system. The concept of specific orbital energy, the energy per unit mass, allows us to compare orbits of different objects easily. Two objects in the same orbit around the same body have the same specific orbital energy, regardless of their masses. This means that a tiny grain of dust and a massive spacecraft in identical orbits around Earth are moving with the same speed and have the same orbital period. Mass does not determine the orbit. Only the gravitational field and the object's velocity do. This is a deeply calming fact. In the realm of orbits, all objects are treated equally by gravity. A feather and a hammer released in orbit around the moon would follow identical paths, as astronauts demonstrated during the Apollo missions. Gravity does not discriminate, and the motion it produces is universal and impartial. The stability of orbits over billions of years also depends on the absence of significant non-gravitational forces. In a vacuum of space, there is no air resistance to slow a planet down, no friction to drain its energy. A planet in orbit experiences only the gravitational pull of the sun and the gentle perturbations from other planets. Because these forces are conservative, meaning they do not dissipate energy, the planet can continue in its orbit indefinitely. This is why the planets have been orbiting the sun for over 4.5 billion years without any need for refueling or maintenance. The orbits are self-sustaining, perpetual motion machines in the truest sense, driven by the curvature of space-time and the inertia of the planets themselves. There is something profoundly peaceful about this. The universe, left to itself, naturally produces stable, enduring structures. Even in regions where non-gravitational forces do exist, such as the upper reaches of Earth's atmosphere, the effects are predictable and manageable. Satellites in low Earth orbit experience a tiny amount of atmospheric drag, which gradually saps their orbital energy and causes them to spiral slowly inward. Over months or years, depending on the altitude and the satellite's shape, this drag will eventually cause the satellite to re-enter the atmosphere and burn up. But this process is slow and well understood, and satellites can be placed in higher orbits where drag is negligible, allowing them to remain in space for centuries or longer. The International Space Station, orbiting at about 400 kilometers altitude, requires periodic boosts to counteract drag and maintain its orbit. These boosts are gentle nudges, small burns of rocket engines that add just enough energy to compensate for the losses. The station's orbit is carefully monitored and adjusted, a human-made extension of the natural principles of orbital mechanics. Geostationary satellites, orbiting at about 35,786 kilometers above the equator, experience almost no atmospheric drag and can remain in their orbits for millions of years if left undisturbed. These satellites orbit with a period of exactly 24 hours, matching Earth's rotation, so they appear to hover motionless above a fixed point on the equator. This makes them ideal for communication and weather observation, as ground antennas can be pointed at a fixed spot in the sky. The geostationary orbit is a special case of a geosynchronous orbit, and it exists at only one altitude for any given planet. For Earth, that altitude is determined by the balance between gravitational pull and the centrifugal effect of the satellite's motion. The fact that such an orbit exists, stable and predictable, is a gift of orbital mechanics, a natural parking spot in the sky where satellites can reside for decades with minimal intervention. The concept of orbital families extends beyond individual planets and moons to include groups of objects that share similar orbital characteristics. The asteroid belt, for instance, contains millions of small bodies orbiting the Sun between Mars and Jupiter, most of them following relatively circular, low-inclination orbits. Within this population, certain regions are nearly empty, cleared out by resonances with Jupiter, while other regions are more densely populated. Some asteroids, known as Trojans, share Jupiter's orbit but remain about 60 degrees ahead of or behind the planet, trapped in stable regions called Lagrange points. These points, labeled L4 and L5, are locations where the gravitational pull of the Sun and Jupiter combine with the centrifugal effect of the orbit to create a stable equilibrium. Objects placed at these points tend to stay there, oscillating gently around the equilibrium position. Jupiter has thousands of Trojan asteroids, and similar populations have been found associated with other planets, including Earth, Mars, and Neptune. The existence of these stable regions is another common feature of orbital mechanics. The gravitational landscape is not uniform, but contains pockets of stability where objects can reside safely for billions of years. The Lagrange points are named after the Italian-French mathematician Joseph Louis Lagrange, who studied the three-body problem in the 18th century. In addition to L4 and L5, there are three other Lagrange points, labeled L1, L2, and L3. These lie along the line connecting the two massive bodies. L1 is between them, L2 is beyond the smaller body, and L3 is on the opposite side of the larger body. Unlike L4 and L5, these 3 points are unstable equilibria, meaning that objects placed there will drift away unless actively controlled. However, with small periodic adjustments, spacecraft can be kept near these points, and several space observatories have been positioned at the Earth-Sun L2 point, about 1.5 million kilometers from Earth. At this location, a spacecraft can keep Earth, the Sun, and the Moon all in the same direction, making it easier to shield sensitive instruments from their light and heat. The James Webb Space Telescope resides in a halo orbit around L2, gently circling the equilibrium point while maintaining a stable thermal environment. The use of Lagrange points is a beautiful example of how understanding orbital mechanics allows us to find and exploit natural havens in space. The concept of orbital perturbations also includes the effects of solar radiation pressure, a subtle force that becomes significant for objects with large surface areas relative to their masses. Photons from the Sun carry momentum, and when they strike a surface, they exert a tiny push. For large spacecraft with reflective solar panels, or for dust grains in space, this pressure can gradually alter orbits over time. Solar sails, experimental spacecraft designed to be propelled by sunlight alone, rely on this principle. By adjusting the angle of a large, reflective sail, a spacecraft can change its orbit without using any fuel, powered only by the steady stream of sunlight. The acceleration is extremely gentle, but over weeks and months, it can produce significant changes in velocity and trajectory. Solar sails represent a poetic fusion of light and motion, a way to navigate the solar system using nothing but the sun's glow. Another subtle effect in orbital mechanics is the Yarkovsky effect, which causes small asteroids to drift slowly in their orbits due to the way they absorb and re-radiate sunlight. When an asteroid is heated by the sun, it does not radiate that heat uniformly in all directions. Because the asteroid is rotating, the warmest part of its surface is typically the afternoon side, which radiates more heat in a direction that has a component along or against the asteroid's orbital motion. This creates a tiny thrust that, over millions of years, can cause the asteroid's orbit to expand or contract. The Yarkovsky effect is so subtle that it was only confirmed observationally in the early 21st century, but it plays a significant role in the long-term evolution of asteroid orbits and in the delivery of meteorites to Earth. It is a reminder that even the faintest forces, acting patiently over deep time, can reshape the architecture of the solar system. The study of orbital mechanics also extends to the motion of artificial satellites and the planning of space missions. Every spacecraft trajectory is carefully designed using the principles of orbital mechanics, with engineers calculating the precise burns needed to reach a destination, enter orbit, or return to Earth. The Hohmann transfer orbit, for example, is an efficient way to move a spacecraft from one circular orbit to another. It involves two engine burns, one to enter an elliptical transfer orbit and another to circularize the orbit at the destination. This method minimizes fuel consumption and is used for missions to other planets and for moving satellites between orbits around Earth. The calculations are exact and the trajectories are predictable, allowing mission planners to send spacecraft across millions or billions of kilometers with remarkable precision. The success of interplanetary missions, from the Voyager probes to the Mars rovers, is a testament to our deep understanding of orbital mechanics and the reliability of its predictions. Gravity assists, also known as gravitational slingshots, are another elegant application of orbital mechanics. When a spacecraft flies close to a planet, it can gain or lose speed relative to the sun by exchanging momentum with the planet. From a spacecraft's perspective, it simply falls toward the planet and then climbs back out of the gravity well. But because the planet is moving in its orbit, the spacecraft trajectory is bent and its velocity relative to the sun changes. The planet's orbit is also affected, but because the planet is so much more massive, the change is immeasurably small. By carefully planning the timing and geometry of these flybys, mission planners can send spacecraft to distant targets that would otherwise be unreachable with available fuel. The Voyager spacecraft used gravity assists at Jupiter and Saturn to reach Uranus, Neptune, and eventually interstellar space. The Cassini mission used flybys of Venus, Earth, and Jupiter to reach Saturn. Each maneuver is a precise dance, a way to borrow energy from the planets and redirect it toward exploration. The predictability and repeatability of these maneuvers are a source of quiet confidence. We can navigate the solar system not by brute force, but by understanding and working with the natural rhythms of orbital motion. The concept of escape velocity also finds practical application in space exploration. To leave Earth and travel to another planet, a spacecraft must reach a speed of about 11.2 kilometers per second relative to Earth's surface. This is Earth's escape velocity, the minimum speed needed to break free from Earth's gravitational pull without any further propulsion. Once a spacecraft reaches this speed, it is no longer bound to Earth and can coast through space. Following an orbit around the Sun, different bodies have different escape velocities, depending on their mass and radius. The Moon's escape velocity is only about 2.4 kilometers per second, which is why the Apollo lunar modules needed much less fuel to leave the Moon than to leave Earth. The sun's escape velocity at Earth's distance is about 42 kilometers per second. But because Earth is already moving at 30 kilometers per second in its orbit, a spacecraft leaving Earth only needs to gain an additional 12 kilometers per second or so to escape the solar system entirely. These calculations are straightforward applications of orbital mechanics, and they allow us to plan missions with confidence, knowing exactly how much energy is required to reach any destination. The concept of orbital inclination becomes particularly important when planning missions to other planets. Most planets orbit the Sun in nearly the same plane, the ecliptic, but their orbits are tilted by a few degrees relative to one another. A spacecraft traveling from Earth to Mars, for example, must account for the slight difference in orbital planes, which requires a small amount of fuel to adjust the inclination. Missions to Mercury or Pluto, which have higher inclinations, require more energy to match the target's orbital plane. The timing of launch windows is also determined by orbital mechanics. The relative positions of Earth and the target planet must be favorable, which typically occurs only once every year or two. These windows are calculated years in advance, and missions are planned around them. The predictability of planetary orbits makes this possible, allowing us to know exactly where each planet will be decades into the future. The long-term stability of the solar system has been a subject of study for centuries, and modern computer simulations have provided reassuring answers. While the orbits of the planets do experience small variations due to mutual gravitational perturbations, these changes are generally bounded and do not lead to catastrophic instability. Simulations run forward for billions of years show that the orbits of the outer planets, from Jupiter to Neptune, remain stable and well separated. The inner planets, being lighter and more closely spaced, experience larger relative perturbations. But even here, the system appears stable over timescales comparable to the age of the solar system. There is a small probability, estimated at around 1%, that Mercury's orbit could become unstable over the next few billion years, potentially leading to a collision with Venus or ejection from the solar system. But such an event is far in the future and unlikely. For practical purposes, the solar system is a stable, predictable clockwork, and we can rest easy knowing that the planets will continue their quiet orbits for eons to come. The study of exoplanetary systems has revealed that not all planetary systems are as stable as ours. Some systems contain planets in highly eccentric or closely spaced orbits that suggest recent dynamical upheaval. These systems may be young, still settling into their final configurations, or they may have experienced disruptive events such as the ejection of a planet or a close encounter with a passing star. The diversity of exoplanetary architectures suggests that planetary system formation and evolution are complex processes with many possible outcomes. Yet even in these systems, the fundamental principles of orbital mechanics apply, and the planets that remain are those whose orbits have found a stable balance. The universe naturally selects for stability, and over time, chaotic systems either settle into order or disintegrate. The concept of mean motion, the average angular speed of a planet in its orbit, provides a useful way to describe and compare orbits. A planet's mean motion is inversely related to its orbital period. Planets that orbit quickly have high mean motions, while distant planets with long periods have low mean motions. Mean motion resonances occur when the ratio of two planets' mean motions is a simple fraction, such as 2 to 1 or 3 to 2. These resonances can be either stabilizing or destabilizing, depending on the specific configuration and the eccentricities of the orbits. In general, resonances that involve small integer ratios and low eccentricities tend to be stable, while those involving higher ratios or high eccentricities can lead to chaotic behavior. The solar system contains several examples of stable resonances, such as Neptune and Pluto, and these resonances have persisted for billions of years, a testament to the robustness of the underlying dynamics. The concept of orbital nodes, the points where an orbit crosses a reference plane, is important for understanding the three-dimensional structure of planetary systems. For planets orbiting the Sun, the reference plane is usually the ecliptic, and the nodes are the points where the planet's orbit crosses this plane. The longitude of the ascending node specifies the direction of one of these crossing points, and it is one of the 6 orbital elements needed to fully describe an orbit. The nodes precess slowly over time due to gravitational perturbations, meaning that the orientation of the orbit in space gradually changes. This precession is another example of the long-term, gentle evolution of orbits under the influence of gravity. The fact that we can predict and measure these changes with high precision is a source of quiet satisfaction, a confirmation that the universe operates according to consistent, knowable laws. The beauty of orbital motion extends beyond individual planets to entire systems of bodies moving in coordinated patterns. When we look at satellite systems around giant planets, we find families of moons performing intricate dances, each one locked into its own stable path. Jupiter's Galilean moons, for instance, move in a carefully balanced arrangement where Io completes 4 orbits for every 2 of Europa and every 1 of Ganymede. This 3-body resonance creates a rhythm that has persisted for billions of years, a celestial music playing in silence. The moons tug on each other, but rather than destabilizing their paths, these tugs reinforce the pattern, keeping each moon in its proper place. It is a self-correcting system, a harmony that needs no conductor, only the patient mathematics of gravity. And within this harmony lies a profound stability. The resonances between moons are not fragile coincidences, but stable configurations that resist disruption. If a small asteroid were to nudge one of these moons slightly, the gravitational interactions with its neighbors would gradually restore the original pattern. The system remembers its rhythm. This resilience is built into the geometry of orbital motion itself. Bodies in resonance occupy regions of phase space where their combined gravitational influences create valleys of stability. And like a ball settling into a bowl, the moons naturally return to these configurations after disturbances. It is a comforting thought, this idea that celestial systems possess an inherent memory, a tendency to return to their preferred states of motion. The concept of phase space itself offers a calming perspective on orbital motion. Phase space is an abstract mathematical realm where each possible state of a system, each combination of position and velocity, corresponds to a single point. The orbit of a planet traces a smooth curve through this space, and as long as no external forces intervene, the planet follows this curve endlessly, never deviating. In phase space, an orbit is not a repeating journey, but a single, eternal path, a thread woven into the fabric of possibility. Looking at orbits this way reveals their true nature as timeless geometric objects, patterns that exist outside the flow of time, waiting to be traced by matter moving through space. This timeless quality extends to the entire solar system. When we map all the planets, asteroids, moons, and comets in phase space, we see a complex tapestry of interwoven curves, each one distinct, each one stable in its own region. The solar system is not a chaotic jumble, but an organized structure, a sculpture carved by gravity into the space of all possible motions. And this sculpture has been remarkably stable for billions of years. The same patterns we observe today existed when the first life appeared on Earth, when the dinosaurs walked, when our ancestors looked up at the night sky. The orbits are older than mountains, older than oceans, older than continents. They are among the most enduring structures in our cosmic neighborhood. The stability of orbits also means that the future is, in many ways, as knowable as the past. We can calculate where Mars will be 1,000 years from now with remarkable precision. We can predict the positions of the outer planets millions of years into the future. This predictability is a rare gift in a universe often governed by quantum uncertainty and chaotic dynamics. Orbital motion is one realm where determinism still reigns, where the future unfolds according to clear, comprehensible rules. There is something deeply reassuring about this. In a world of constant change and uncertainty, the planets move along their appointed paths, indifferent to the passage of time, faithful to the laws that govern them. Even the small irregularities in planetary motion, the perturbations and wobbles we have discussed, follow predictable patterns. The precession of Mercury's orbit, for instance, advances at a steady rate, completing a full cycle every 225,000 years or so. We can model this precession, account for it, predict it. The same is true for the slow changes in Earth's axial tilt and orbital eccentricity. These variations unfold over tens of thousands of years, but they follow cycles we can calculate and understand. The Milankovitch cycles, named after the Serbian scientist who studied them, describe how Earth's orbital parameters change over time and how these changes influence climate. Even something as complex as ice ages can be connected to the gentle, predictable variations in our planet's orbit. This connection between orbital mechanics and Earth's climate reminds us that we are not separate from the celestial motions around us. The tilt of our planet, the shape of our orbit, the timing of our seasons, all are products of gravitational interactions playing out over cosmic timescales. When Earth's orbit becomes slightly more elliptical, our planet experiences greater variation in the amount of sunlight received throughout the year. When the axial tilt increases, the seasons become more extreme. These changes happen slowly, too slowly for any human to notice in a lifetime. But over millennia, they reshape the climate, advance and retreat glaciers, alter the distribution of life. We live within the consequences of orbital motion, our existence shaped by the same forces that guide planets around the sun. And yet, for all this influence, orbital motion remains gentle. The changes it brings unfold gradually, giving life time to adapt, ecosystems time to shift. There are no sudden jolts, no abrupt catastrophes inherent in the normal motions of planets. The variations are smooth, the cycles are long, and the overall pattern is one of stability. This is the nature of gravity's influence. It is patient, persistent, and ultimately reliable. It does not hurry, does not force, but simply guides, allowing matter to find its natural paths through space. The same principles that govern planetary orbits also apply to artificial satellites circling Earth. Every satellite, from the smallest CubeSat to the largest space station, follows an elliptical path determined by its velocity and altitude. The International Space Station, for example, orbits at an average altitude of about 400 kilometers, completing one orbit roughly every 90 minutes. At this altitude, there is still a trace of Earth's atmosphere, and this thin air creates a tiny amount of drag, gradually slowing the station and causing its orbit to decay. To counteract this, the station must periodically boost itself to a higher altitude using thrusters. This is one of the few cases where an orbit requires active maintenance, a reminder that in the inner regions of a planet's gravitational well, other forces can intrude. But even this orbital decay follows predictable laws. Engineers can calculate exactly how much altitude the station loses each day and plan the necessary boosts accordingly. The process is gentle and manageable, not a sudden plunge, but a gradual spiral that can be corrected with small adjustments. This predictability makes spaceflight possible. We can launch satellites into precise orbits, knowing they will remain there, performing their functions for years or even decades. Communication satellites in geostationary orbit, weather satellites in polar orbits, GPS satellites in medium Earth orbit, all rely on the stability and predictability of orbital motion. Geostationary orbits, in particular, offer a beautiful example of orbital harmony. At an altitude of approximately 35,786 kilometers above Earth's equator, a satellite takes exactly 24 hours to complete one orbit, matching Earth's rotation. From the ground, such a satellite appears to hover motionless in the sky, always in the same position relative to the surface. This synchronization is not forced or artificial, but a natural consequence of orbital mechanics. At that specific altitude, the balance between gravitational pull and orbital velocity produces a period that matches Earth's day. It is a resonance, a place where two rhythms align, creating a stable, useful configuration. Dozens of satellites occupy this orbital ring, providing constant communication links, broadcasting signals, monitoring weather. They are held there not by engines or supports, but by the same gravitational principles that have guided planets for billions of years. The concept of orbital families extends beyond planets and moons to include asteroids and comets. Many asteroids occupy specific orbital zones, grouped by similar characteristics. The Trojan asteroids, for instance, share Jupiter's orbit, clustered around the L4 and L5 Lagrange points, 60 degrees ahead of and behind the giant planet. These stable regions collect debris over time, creating populations of asteroids that travel alongside Jupiter, never colliding with it, held in place by the balance of gravitational forces. There are thousands of Trojan asteroids, a silent entourage accompanying Jupiter on its 12-year journey around the Sun. Other planets have Trojans as well: Neptune, Mars. Even Earth has at least one known Trojan asteroid. These objects are reminders that orbital space is not empty, but populated, structured, organized into families and groups by the invisible architecture of gravity. Comets, too, follow orbital paths, though often much more elongated than those of planets. A typical long-period comet might spend thousands of years traveling outward from the Sun, moving slowly through the cold darkness of the outer solar system, before gravity gently turns it around and it begins the long fall back toward the inner warmth. As it approaches the Sun, solar radiation heats the comet's icy surface, releasing gas and dust that form the characteristic glowing coma and tail. But even this dramatic display is part of a predictable orbital cycle. Each time the comet passes the Sun, it loses a bit of its mass, but its orbit remains governed by the same laws. Some comets have been observed for centuries, their returns predicted with precision. Halley's Comet, for instance, completes an orbit every 75 to 76 years, and its appearances have been recorded for over 2 millennia. It is a reliable visitor, a traveler on a well-worn path, returning again and again to the inner solar system. The orbits of comets also reveal the vast extent of the Sun's gravitational influence. The Oort cloud, a theoretical shell of icy bodies surrounding the solar system, extends perhaps halfway to the nearest star, a distance of a light year or more. Objects in the Oort cloud are barely bound to the Sun, moving so slowly that their orbital periods may span millions of years. Yet even at these immense distances, they remain in orbit, tethered by gravity's patient pull. The Sun's influence reaches farther than we can easily imagine, a gravitational embrace that extends into the space between stars. And within that vast sphere, every object, no matter how distant, follows an elliptical path, a testament to the universality of orbital motion. This universality is one of the most calming aspects of orbital mechanics. The same laws apply everywhere, from the smallest moon to the largest galaxy. A moon orbiting a planet follows the same principles as a planet orbiting a star, which follows the same principles as a star orbiting the center of a galaxy. Gravity does not change its nature with scale. It is always an inverse square force, always attractive, always patient. This consistency means that once we understand orbital motion in one context, we understand it in all contexts. The knowledge is transferable, reliable, universal. It is a rare kind of certainty in science, a foundation upon which countless other discoveries rest. Galaxies themselves are, in a sense, collections of orbits. The Milky Way contains hundreds of billions of stars, each one following its own path around the galactic center. Our Sun, along with its family of planets, completes one orbit around the galaxy approximately every 225 million years, a period sometimes called a galactic year. We are moving through space at hundreds of kilometers per second, yet we feel nothing, notice nothing, because everything around us moves together. The stars we see at night are our neighbors in this grand orbital dance, all of us circling the galactic core, all bound by the same gravitational forces. The galaxy is not a static structure, but a dynamic system, a spiral of orbits nested within orbits, a hierarchy of motion extending from planets to stars to the galaxy as a whole. And even galaxies orbit within clusters, and clusters move within superclusters, all governed by gravity, all following paths through space. The universe is a symphony of orbital motion, playing out on every scale, from the smallest asteroid to the largest structures we can observe. This fractal quality, this repetition of patterns at different scales, suggests a deep unity in the workings of the cosmos. The same simple law, gravity decreases with the square of distance, produces all this complexity, all this structure, all this motion. It is elegant, economical, and profoundly beautiful. Returning to our own solar system, we can appreciate how orbital motion connects us to the broader universe. When we watch the planets move across the night sky, we are witnessing the same processes that govern galaxies and galaxy clusters. When we send a spacecraft to another planet, we are applying principles that hold true throughout the cosmos. There is a continuity, a thread of understanding that links the smallest human-made satellite to the grandest structures in the universe. And this thread is woven from the simple, steady pull of gravity, the force that keeps everything in motion, everything in place. The predictability of orbits has also allowed humanity to explore the solar system with increasing confidence. Every mission to another planet begins with careful calculations of orbital mechanics. Engineers determine the optimal launch window, the moment when Earth and the target planet are positioned such that a spacecraft can travel between them with the least expenditure of fuel. These windows open and close according to the planet's orbital periods, creating a schedule that mission planners must follow. For Mars, launch windows occur roughly every 26 months, when Earth and Mars are properly aligned. For outer planets, the windows are less frequent, but equally predictable. This rhythm of opportunity is set by the orbits themselves, a natural calendar written in the motions of worlds. Once launched, a spacecraft follows its own carefully designed orbit, a trajectory that threads through the solar system, sometimes passing close to other planets for gravity assists, sometimes entering orbit around the destination. The entire journey is planned in advance, each maneuver calculated to take advantage of orbital mechanics. The spacecraft becomes, for a time, a new member of the solar system's family of orbiting bodies, subject to the same laws, moving along paths determined by gravity and velocity. And when the mission ends, the spacecraft often remains in orbit, a silent monument to human curiosity, continuing to circle the sun or a distant planet, perhaps for millions of years. Some spacecraft have even left the solar system entirely, or are in the process of doing so. Voyager 1 and Voyager 2, launched in 1977, have traveled beyond the orbit of Neptune, beyond the influence of the solar wind, into interstellar space. Yet even these distant travelers are still, in a technical sense, in orbit around the Sun. Their velocity is not quite enough to escape the Sun's gravity entirely, but they are so far away, moving so slowly relative to the Sun, that they will never return. They are on hyperbolic trajectories, open curves that stretch toward infinity. In tens of thousands of years, they will pass near other stars, still drifting, still moving, still subject to gravity, but no longer bound to any single object. They are the first human-made objects to become wanderers among the stars, and their paths, too, are determined by the principles of orbital motion. The concept of escape velocity, the speed needed to break free from a gravitational pull, is another aspect of orbital mechanics that offers a kind of reassurance. Every object has an escape velocity, a threshold that divides bound orbits from unbound trajectories. For Earth, escape velocity at the surface is about 11.2 kilometers per second. Anything moving faster than this will escape into space, while anything slower will eventually fall back. This threshold is not arbitrary, but emerges naturally from the mathematics of gravity and energy. It represents a boundary, a clear division between staying and leaving, between being held and being free. And yet, it is not a wall or a barrier, but simply a speed, a measure of kinetic energy relative to gravitational potential. It is a soft boundary, crossed by velocity alone. Spacecraft destined for other planets must reach or exceed Earth's escape velocity, and then continue to maneuver within the Sun's gravitational field. They are never truly free of gravity, but are always falling, always in orbit around something. Even in the emptiness of interstellar space, gravity from distant stars and the galaxy itself exerts a pull, however faint. There is no place in the universe entirely free from gravitational influence. Everything is always falling, always orbiting, always in motion. This universality of gravitational interaction means that the concept of orbit is not limited to planets and moons, but extends to every particle of matter in the cosmos. We are all in orbit around something, all part of the vast, interconnected web of gravitational relationships that defines the structure of the universe. This interconnectedness extends to the very fabric of space-time itself. According to general relativity, gravity is not a force in the traditional sense, but a curvature of space-time caused by mass and energy. Planets orbit the Sun not because they are pulled by an invisible force, but because they follow the straightest possible paths through curved space-time. In this view, an orbit is a geodesic, a natural path that requires no force to maintain. A planet in orbit is not being pushed or pulled, but is simply moving freely through a curved geometry. This perspective transforms our understanding of orbital motion from a dynamic process involving forces to a geometric process involving the shape of space itself. It is a subtle shift, but one that reveals the deep elegance of the universe's design. In curved space-time, the orbit of a planet is as natural as a straight line in flat space. The planet is not fighting against gravity or being held in place by a balance of forces. It is simply following the contours of space-time, moving along a path that feels, to the planet itself, like traveling in a straight line. This is why astronauts in orbit experience weightlessness. They're in free fall, following a geodesic through space-time, and there is no sensation of force, no feeling of being pulled. They are at rest in their own reference frame, even as they circle the Earth at thousands of kilometers per hour. This is the true nature of orbital motion. It is a state of free fall, a natural, effortless glide through the geometry of space. The mathematics of general relativity also predicts subtle effects that Newtonian mechanics cannot fully explain. The precession of Mercury's orbit, for instance, is slightly faster than Newton's laws predict. The difference is small, only about 43 arcseconds per century, but it is measurable and significant. Einstein's theory of general relativity accounts for this extra precession by including the curvature of space-time near the Sun. The closer a planet orbits to a massive object, the more pronounced these relativistic effects become. For most planets, the corrections are negligible, but for Mercury, orbiting close to the Sun, they are just large enough to detect. This tiny discrepancy was one of the first confirmations of general relativity, a triumph of theory and observation, and a reminder that even the most familiar motions, like planetary orbits, can reveal profound truths about the nature of reality. Another prediction of general relativity is the existence of gravitational waves, ripples in space-time caused by accelerating masses. When two massive objects, such as black holes or neutron stars, orbit each other closely, they emit gravitational waves, losing energy in the process. This energy loss causes the orbit to gradually shrink, and the objects spiral inward, eventually merging. The first direct detection of gravitational waves, announced in 2016, came from a merger of two black holes, an event that occurred over 1 billion years ago. The signal recorded by detectors on Earth was a faint chirp, the sound of space-time itself vibrating as two immense objects completed their final orbits and collided. This observation confirmed another aspect of orbital mechanics, showing that even in the most extreme environments, the principles of motion and gravity hold true. Orbits are not just paths through space, but also sources of waves in the fabric of reality itself. These gravitational waves carry energy away from orbiting systems, causing them to decay over time. For ordinary planets and stars, this effect is incredibly weak, far too small to measure or matter. Earth's orbit, for example, loses energy to gravitational waves, but the rate is so slow that it would take longer than the age of the universe for any noticeable change to occur. The effect only becomes significant for extremely massive objects orbiting very closely, such as pairs of neutron stars or black holes. In these systems, the emission of gravitational waves can cause the orbit to shrink noticeably over thousands or millions of years, eventually leading to a merger. This is one of the few processes that can cause a stable orbit to decay on its own, without external perturbations. Yet, even this decay follows predictable laws, governed by the equations of general relativity, unfolding according to a precise mathematical script. The study of binary star systems has revealed much about orbital mechanics in extreme conditions. Many stars exist in pairs, orbiting a common center of mass, bound together by gravity. Some of these systems are so close that the stars nearly touch, completing an orbit in a matter of hours. Others are widely separated, taking centuries to complete a single orbit. In all cases, the motion follows Kepler's laws, adapted for the two-body problem. The stars pull on each other, each one orbiting the barycenter, each one influencing the other's path. In some systems, the stars are so close that they exchange material, with gas flowing from one star to the other, altering their masses and their orbits over time. These interactions can be complex, but they remain grounded in the fundamental principles of gravity in motion. Eclipsing binary stars, where the orbital plane is aligned with our line of sight, provide a natural laboratory for studying orbital mechanics. As the stars orbit, they periodically pass in front of each other, causing regular dips in the system's brightness. By measuring the timing and depth of these eclipses, astronomers can determine the star's orbital period, their sizes, their masses, and even their shapes. The regularity of the eclipses reflects the regularity of the orbit, a clockwork precision that allows for detailed analysis. Some eclipsing binaries have been monitored for over a century, and their orbits show remarkable stability, changing only in predictable ways due to known effects like precession or tidal interactions. They are cosmic metronomes, keeping time with their orbital motion, reliable and steady. The discovery of exoplanets, planets orbiting stars other than the Sun, has expanded our understanding of orbital mechanics to thousands of new systems. These distant worlds orbit their stars just as our planets orbit the Sun, following elliptical paths governed by the same laws. Some exoplanets have been found in highly eccentric orbits, swinging close to their stars and then far away, experiencing extreme variations in temperature and radiation. Others orbit in tight, circular paths, completing a year in just a few Earth days. There are planets in resonance with each other, planets that migrate inward or outward over time, planets in binary star systems orbiting both stars at once. The diversity of exoplanetary orbits is astonishing, yet all of them obey the same fundamental principles. Gravity is universal, and orbital motion is its signature. One particularly calming aspect of exoplanet research is the realization that planetary systems are common. Nearly every star we observe appears to host planets, and many of these systems contain multiple worlds in stable, long-lasting orbits. The universe is full of planetary systems, each one a miniature solar system, each one a testament to the organizing power of gravity. This abundance suggests that the formation of planets and the establishment of stable orbits are natural, inevitable outcomes of star formation. Wherever there is a star, there is likely a family of worlds circling it, each one tracing its own ellipse through space, each one part of a gravitational dance that has been unfolding for billions of years. The study of orbital motion also connects to the search for life beyond Earth. The habitable zone, the region around a star where conditions might allow liquid water to exist on a planet's surface, is defined by orbital distance. Too close, and water evaporates. Too far, and it freezes. But within a certain range, determined by the star's luminosity and the planet's atmosphere, liquid water, and potentially life, can persist. Earth orbits comfortably within the Sun's habitable zone, and our stable, nearly circular orbit helps maintain a relatively constant climate over long periods. This stability has allowed life to evolve, adapt, and thrive. Other planets and other systems may enjoy similar stability, their orbits keeping them in the sweet spot where life can flourish. The search for such worlds is, in part, a search for stable orbits and habitable zones, a search for places where the conditions for life are maintained by the gentle, predictable motion of planets around their stars. The concept of the habitable zone is not fixed but changes as a star ages. Stars gradually brighten over billions of years, and as they do, the habitable zone moves outward. Earth, for instance, was cooler in the distant past when the Sun was younger and dimmer. In the far future, the Sun will continue to brighten, and eventually Earth may become too hot to support life as we know it. But this change happens slowly over hundreds of millions of years, giving life time to adapt or perhaps to migrate. The motion of the habitable zone is another example of the slow, patient changes that characterize orbital and stellar evolution. Nothing happens suddenly. Everything unfolds according to the rhythms of cosmic time. This patience, this slowness, is one of the most comforting aspects of orbital mechanics. The universe is not in a hurry. Planets take years, decades, or centuries to complete their orbits. Orbital parameters change over thousands or millions of years. Gravitational interactions play out over timescales that dwarf human history. There is no rush, no urgency, only the steady, inexorable progression of motion governed by immutable laws. In a world where so much feels fast and chaotic, the slow, predictable motion of celestial bodies offers a sense of permanence and peace. The planets will continue their orbits long after we are gone, tracing the same ellipses, following the same paths, indifferent to the passage of time. And in this indifference lies a strange comfort. The universe does not demand our attention or our understanding. It simply is unfolding according to its own logic, following rules that were set in motion billions of years ago. We are privileged to observe it, to study it, to find patterns and meaning in its motions. But the universe itself does not depend on us. The planets would orbit the sun whether or not anyone was here to watch. The stars would circle the galaxy. The galaxies would drift through space, all according to the same principles, all following the same paths. There's a humility in this realization, a recognition that we are part of something much larger and much older than ourselves. And there is also a reassurance. The universe is stable, orderly, and predictable. It will continue to be so long into the future, a vast, patient machine of gravity and motion, turning without effort, without end. As we consider the orbits of planets, moons, asteroids, comets, stars, and galaxies, we see a universe organized by gravity into a hierarchy of motion. Each orbit is a loop in a vast, interconnected web, each body influencing and influenced by others, yet each following its own distinct path. The web is dynamic but stable, complex but comprehensible. It is a structure built from the simplest of forces, applied universally, creating patterns that repeat across scales and across time. And at the heart of it all is the ellipse, the fundamental shape of orbital motion, a curve that has been traced by countless bodies over billions of years, a shape that will continue to define the paths of worlds for billions more. The ellipse itself is a shape of balance and harmony. It is defined by two foci, and for any point on the ellipse, the sum of the distances to the two foci is constant. In a planetary orbit, one focus is occupied by the sun, and the other is empty, a mathematical point in space. Yet this empty focus plays a role in the geometry, ensuring that the orbit maintains its shape, its proportions. The ellipse is not arbitrary, but emerges naturally from the inverse square law of gravity and the conservation of energy and angular momentum. It is the only shape that satisfies all the constraints, the only curve that allows a body to orbit indefinitely without spiraling inward or escaping outward. In this sense, the ellipse is the shape of stability, the form that gravity prefers, the path that requires no correction, no adjustment, no intervention. It is a perfect solution to the problem of motion under gravity, elegant in its simplicity, eternal in its application. And so, as we think about planetary orbits in motion, we are invited to relax into the knowledge that the universe is, at its core, a place of order. Gravity guides without force, shapes without effort, creates stability without rigidity. The planets move along their paths not because they must, but because it is the natural thing to do, the easiest path through the curved landscape of space-time. There is no struggle, no resistance, only the smooth, continuous glide of matter through space, following the contours laid down by mass and energy. It is a dance that has been going on since the beginning, a motion that will continue until the end, a rhythm that underlies all the complexity and diversity of the cosmos. In this dance, we find a reflection of the principles that govern not just planets, but all things: balance, harmony, predictability, and patience. The same forces that keep Earth in its orbit also shape the cycles of day and night, the seasons, the tides. They connect us to the sun, the moon, the other planets, and ultimately to the entire universe. We are participants in the orbital dance, inhabitants of a world that is itself in motion, part of a system that is part of a galaxy that is part of a universe, all moving, all orbiting, all held together by gravity's gentle, persistent pull. And as you rest, as you let these thoughts settle softly in your mind, you can take comfort in the knowledge that the universe is a stable place, governed by laws that do not change, following patterns that endure. The planets will rise and set, the stars will wheel across the sky, and the great cycles of motion will continue, unhurried and untroubled. You are safe within this vast, orderly system, a small part of something immense and beautiful, something that has been unfolding for billions of years and will continue for billions more. There is no need to worry, no need to hurry. The universe moves at its own pace, and you can rest in the certainty that it will still be here, still turning, still following its ancient paths when you wake.